Hi guys, let's take a look at this question. They gave us a graph of first ionization energy. We have the atomic number on the x-axis and the ionization energy on the y-axis. Then they ask us to define ionization energy. So ionization energy is the energy needed per mole to remove an electron from an atom in a gaseous phase. 3.2. State the general trend in ionization energy from the left to the right across a period on the periodic table. So, ionization energy from the left to the right on the periodic table. Ionization energy will increase from the left all the way to the right. So, you will write ionization energy increases from the left to the right. The right increases so you can understand. The increases left to right. 3.3. There is a drop in ionization energy from beryllium to boron. So let's just go look at the periodic table. There's beryllium, there's boron. There's a drop in ionization energy. So beryllium, boron. There we go. All right. Write down the SP notation for beryllium and for boron. Okay. So 3.3.1, the SP notation of beryllium and the SP notation of boron. Okay, so let's go look at our periodic table. So where is boron? Boron is right here. And in a previous video, I've done examples of SP notations, right? So remember, the first line is your 1s, that line. Then you have your second line. You have your first block here, which is called your S block. And still in the same line, you have your P block. All right. Then again, you have your third line and your S block. And you have still your third line and your P block, right? This block I'm talking about is your P block. All the way there. That's your P block, right? All right. Now we need to get the SP notation of beryllium. So we need to write down all the electrons up until beryllium. Okay. So we have 1s. How many electrons is there in 1s? 1 and 2. 1 and 2. So we're going to have, just going to write it on this slide. Beryllium is 1s2. Then beryllium is in the second line in the S block. How many electrons to get to beryllium? 1 and 2. So we have 2s2. Perfect. Now for boron. Where is boron? Boron is right there. So now we do the same process for boron. I'm going to use the red color. So we need to get to boron. We start with 1s. Again, there's 1, 2. Then we in our second line at the S block, 1 and 2. And then boron is in the P block. So we have 2p. How much to get to boron? Only 1. So it's going to be 2p1. And that is going to be the SP notation of boron. Then they ask, explain this drop in ionization energy. So why is there a drop from beryllium to boron in ionization energy? Okay, so that is because boron has a 2p energy level. And 2p is a higher energy level than 2s. So let me show you. We just did that. Boron has a 2p level and it's higher than an S level like in beryllium, right? Therefore, less energy is needed to remove the valence electrons from beryllium from boron as from beryllium. Okay, let me just repeat that. So because boron has a 2p energy level, right? And beryllium only has a 2s level. Because 2p is a higher energy level than 2s, boron will need less energy to remove the valence electrons than beryllium. Okay, does that make sense? I hope it does. You can't answer me. Okay, 3.4. Is the following statement true or false? If false, rewrite the statement correctly. The ionization energy of noble gases is high because of the half-filled S and P orbitals. The answer is false. The ionization energy of noble gases is high because of the filled, so not half-filled, of the filled S and P orbitals. 3.5. Study the ionization energy of group 1 elements in the graph above and answer the questions that follow. Give the general name of group 1 elements. Group 1 elements are right here. What do we call group 1 elements? We call them alkali metals. So alkali metals. 3.5.2. State the trend in the reactivity of elements in group 1. In group 1, reactivity increases from top to bottom. That's the reactivity in the group 1. Explain the reason for this trend by using the graph of ionization of energy. Okay, so remember, do we see here group 1 elements? We have hydrogen, lithium, sodium, and potassium. Hydrogen, lithium, sodium, potassium. Do we see there's a decrease in ionization energy, right? So the ionization energy decreases. And when ionization energy decreases, we need less energy to remove an electron. And because we need less energy to remove an electron, reactivity then therefore increases. And that is why the trend is from top to bottom. And that is it, guys. See ya.